Dr. D.
Hi.
Hi, guys.
Can you tell us what lightning is?
Sure. Wait a minute, what brings this up?
Well, I was telling Kaylee and Jacob that the power is still out across the street, but it's still on in our treehouse. We're trying to figure out why.
Where are you going to start?
We came up with a hypothesis. We think that lightning caused a power outage.
It was a pretty big storm last night. How are you going to test your hypothesis?
We're not sure.
Well, to understand lightning, we first need to look at some basics. Let's rip up this paper. Now comb your hair briskly and then bring the comb down close to the paper.
Neat. Why did it do that?
Well, the ancient Greeks noticed the same thing when they rubbed amber with wool.
Who's Amber?
Not who, but what? Amber's fossilized tree sap.
Oh, okay.
The amber picked up little objects like strands of fiber and hair, just like the comb picked up the paper. We say that the comb and the amber are electrically charged.
Can other objects do the same thing?
Sure, this balloon can pick up the paper too.
Wow. And it picks up other things too. Like this rice cereal and salt.
The balloon will also stick to the wall. It can also attract a stream of water. Whoa! If you rub the acrylic rod with the plastic bag, it'll do the same thing. Now, how do you know that the balloon was charged and not the paper?
Well, if an object is electrically charged, it should pick up objects like little pieces of paper or other such objects. Let's see. Nothing happened.
Very good. A charged object will pick up other neutral or uncharged objects, but an uncharged object won't. Let's do an experiment with some tape. Bring this bar around. Put some tape on the table. I'll pull it up real quickly. And watch this. It attracted the paper. It must be charged. Now let's try two pieces of tape, one on top of each other. Hold on to that, please. How can we tell if these are charged?
We need to do the paper scraps test to find out.
Let's try it. Yep, they're charged all right. Well, here's the experiment. Let's hang up the single piece of charged tape. I will pull up the double tape. First the top piece.
It attracts the tape, just like before.
It's repelling the second tape. We haven't seen that before.
What conclusions can you make?
Well, if an object is charged, it attracts uncharged items, but it may attract or repel other charged items.
Does that mean there are two types of charges?
That's right. Two types of charges are positive and negative. The top piece and the bottom piece have different charges. Now let's do this again. This time we'll take both pieces of tape in exactly the same way. So
They must have the same charge.
that's right. Will they attract or repel?
They repel. Let's see. If the charges are different, then they must attract. Let's find out.
All right, we use the two tapes again. Both have different charges. How about that? Look at this machine. It's called a Van de Graaff generator. Jacob, stand up on the stool if you would, and put your hands on top. I'm going to turn this machine on and transfer a lot of charge into you. It won't shock you, I promise.
Wow, his hair is really standing up.
Is it because all my hair is charged the same way and each strand is repelling or pushing away from the strand next to it?
That's right. In the beginning, your body was neutral. It had the same number of positive and negative charges. We call the positive charges protons, the negative charges electrons. And we transfer an awful lot of negatively charged electrons into your body. What kind of charge would you have then?
Well, if the number of electrons and protons in his body were the same, then they would basically cancel each other out. And then if we added a lot of electrons, then I guess his body would be negatively charged.
That's right.
And I always thought you were the negative one.
Now, if we turn the thing on again, build up a huge charge on top, move the second ball closer to the first. Wow, it looks just like lightning. Now, what's going on there?
Well, the electrons are jumping from the Van de Graaff to the ball.
It looks more like a flash of light than a bunch of particles.
Well, I learned that you can't see electrons, so how can we see these electrons?
Well, you're right, electrons are too small to see. As the electrons jump from the Van de Graaff to the ball, they heat up the air and cause it to glow. What you're seeing is the glowing air, not the moving electrons.
Is this how lightning works?
Yes, it's very similar.
So, Dr. D, did we get electricity from lightning?
Not quite. I'll tell you what. I'm going to line you up with a researcher from NASA Langley Research Center in Hampton, Virginia. His name is Bruce Fisher. He's done a lot of studies on lightning. I'll arrange for you to meet him at the Virginia Air and Space Center.
Great. Thanks, Dr. D.
So, let's get up and go. Bye, Dr. D.
Bye, guys.
Bye.